All right, let's dive right into this explainer. Whenever we hear about artificial intelligence these days, the conversation is pretty much entirely dominated by software, right? We hear all about large language models, neural networks, generative algorithms, the flashy stuff. But today, we're actually going to look right past that. We're going to examine the hidden, highly complex physical foundation of the AI revolution. Because without the microscopic, incredibly precise physical plumbing, honestly, none of the magic of AI actually happens. To put the scale of this into perspective, take a look at this massive number, $459 billion. By the year 2032, the global AI semiconductor market is projected to hit this absolutely staggering figure, and it's growing at a really rapid compound annual growth rate of 27.5%. This is a fantastic reminder that in any gold rush, the real sustainable money is usually found in selling the shovels. And in the AI gold rush, those shovels are the physical hardware components, the chips, the boards, the high-speed connectors, and the vast networks of data centers.
So here is our roadmap for today. 1. The AI semiconductor boom. 2. Edge AI versus cloud AI. 3. The high-speed data bottleneck. 4. The unsung hero, testing. And finally, number 5, automated manufacturing and beyond.
Okay, let's jump into section 1, the AI semiconductor boom. So, what actually makes these specific chips so uniquely powerful and highly sought after by literally every major tech company on Earth? Well, to understand the boom, we really have to understand the fundamental difference in how these chips think. Traditional CPUs, the processors that have run our laptops for decades, they're designed to process tasks sequentially. They do one thing very fast and then move to the next. But AI requires a totally different approach. AI chips have a parallel computing structure. This allows them to handle massive amounts of mathematical calculations and data all at the exact same time. The most famous of these are GPUs, or graphics processing units. They were originally just for video game graphics, but their high parallel computing power turned out to be exactly what we needed to train AI. Today, we're also seeing highly specialized systems on a chip, or SoCs, and neural processing units, NPUs, that are entirely dedicated to this task. Just take a look at the sheer complexity of this layered architecture on the circuit board. It's not just one flat chip. It's this dense, three-dimensional architectural marvel. The sheer density of the connections required to enable all that parallel processing is honestly staggering. These are the specific circuits that are suddenly powering everything around us, from the natural language processing in your smartphone to the computer vision in self-driving cars, all the way up to the traffic management systems of modern smart cities. Moving right along to section 2, Edge AI versus Cloud AI. Now, depending entirely on where that massive AI processing actually takes place, engineers have to build completely different hardware networks. Edge AI is all about keeping the brain close to the action. The computer doing the processing is physically right there near the user. Think of a smart security camera. It gives you lightning-fast responses, it's localized, and because your data doesn't travel far, there's a much lower risk of information leakage. But it's really meant for smaller-scale tasks. Cloud AI, on the other hand, is the heavy lifter. Your data is sent miles away to massive data centers packed with high-performance servers. This allows for incredibly complex processing that an edge device just couldn't handle, which drastically reduces the load on your actual terminal. Both are absolutely vital, but they require entirely different physical setups. Which brings us to section 3. The high-speed data bottleneck. Here is the ultimate catch in the AI hardware world. Whether you're processing locally on the edge or miles away in the cloud, all of that incredible processing power is completely useless if your data transmission creates a bottleneck. When you look at a cloud AI data center architecture, it's wild how many discrete components have to communicate simultaneously. You've got CPUs talking to memory, CPUs talking to AI accelerators via PCIe switches, storage drives passing data back and forth. Processing huge amounts of data like this requires flawless, uninterrupted, high-speed digital communications. If the connection between the CPU and the AI accelerator lags by even a fraction of a millisecond, the whole system backs up. To prevent that, engineers rely on incredibly strict communication standards to bridge these vital hardware pieces together. PCI connects those crucial AI accelerators and SSDs to the motherboards. DDR is used for main computer memory, while Ethernet bridges the massive gaps between different servers. We even have CCII, the Common Electrical Interface, managing the microscopic data traffic right inside the semiconductor chips themselves. These aren't just random acronyms. These are the strict physical rules of the road. If the hardware fails to perfectly meet these standards, data drops, calculations fail, and the AI system basically crashes. And that leads us to section 4, the unsung hero,
testing.
So, how do we actually guarantee these connections won't fail? Well, we rely on microscopic testing to prove these high speed connections will work out in the real world. To verify this high frequency performance, engineers are absolutely obsessed with evaluating something called S parameters, or scattering parameters. These let engineers quantitatively and accurately understand exactly how the physical materials of the chips and boards affect signal transmission and reflection. Think of it kind of like testing a pipe to see exactly how much water pressure it can handle before it leaks, but instead of water, we're testing the flow of high-speed digital data through microscopic metal pathways. Historically, though, this testing was a nightmare. It was a massive bottleneck in itself. To measure incredibly high frequencies, specifically anything above 110 gigahertz, engineers had to use vector network analyzers, or VNAs. But the process was agonizing. They had to use multiple VNA setups because each had a limited frequency bandwidth. They would literally have to manually swap out millimeter waveguide modules, then take all that fragmented data, dump it into a PC, and try to stitch it together. The result? Frustrating data splices, steps, and continuity errors. It was basically like trying to read a novel where every other page is written in an entirely different language. It really slowed down the development of next-gen AI chips. But a company named Enritsu really revolutionized this whole process. When you look at a conventional stepped measurement graph, you can literally see the problem. The steps, the breaks, the messy gaps in the data where modules had to be physically swapped out. But Enritsu's proprietary millimeter wave module technology enables this ultra-wideband, seamless, single-sweep measurement all the way from 70 kilohertz up to 220 gigahertz. It's just one smooth, continuous line. No waveguide swapping, no data splices, no step errors, just pure, accurate data mapping the entire frequency response in a single go. And this is what the actual physical shovels of the AI boom look like in action. We're talking about an incredibly precise MPI probe station practically hovering over a semiconductor wafer, using dedicated, space-saving probe tips to make physical contact with circuits that are literally smaller than a speck of dust. And that's hooked right up to a vector network analyzer, actively evaluating those S parameters we talked about. This is literally the workbench where the reliability of the entire AI revolution is guaranteed. By utilizing these Enritsu testing solutions, from their broadband single-sweep tech to their microscopic 0.6 millimeter coaxial interfaces handling up to 220 gigahertz, manufacturers are finally able to bust through that testing bottleneck. They can accurately measure signal waveforms and bit error rates at completely unprecedented speeds. What you should really take away from this is that better, faster testing directly paves the way for faster, more reliable, and much more capable AI actually making it to market. Let's wrap up with Section 5, Automated Manufacturing and Beyond. Zooming back out to the global scale, we're seeing massive initiatives heavily investing in the physical production of this hardware. Take Saudi Vision 2030, for example, which is really pushing for an industrial revolution in manufacturing. The irony here, and honestly the brilliance of it, is that building the physical hardware for AI now requires its own AI. Modern electronics plants are using highly precise robotic arms, automated printed circuit board assembly lines, and smart robots just to meet the insane global demand for AI infrastructure. AI is literally driving the efficiency required to build more AI. And that brings this whole explainer full circle. We've seen that right beneath the digital magic of AI lies a vast, complex, and intensely physical world of parallel processors, high-speed data connections, microscopic testing probes, and automated factory floors. So I want to leave you with this final thought today. As AI software continues to evolve at this breakneck pace, are we paying enough attention to the physical limits of the hardware, the literal plumbing that makes it all possible? Understanding this hidden infrastructure is the true key to understanding the future of the AI gold rush. Thanks for joining me on this explainer, and definitely keep your eyes on the hardware.